Hi, this is Group 30. My name is Vipul Sarin and we'll be talking about our programming language NanoC. In this video presentation, we'll first take you through the introduction of NanoC. We'll talk about installation and use. We'll move on to NanoC language characteristics. We'll talk briefly about the grammar. We'll talk about NanoC antler parsing. And finally, we will end with sample programs and NanoC runtime. Now, NanoC is a language which emulates a small subset of the C programming language. NanoC is a high-level language which is compiled to a simple assembly-level interpreted language. The language is parsed using top-down recursive descent parsing. In order to create language C, we used Antler, which is a parser generator in Java. It was used for defining the grammar, the lexer, and parser of NanoC. For the runtime, we used Python. So in order to install and use NanoC, in a new folder, unzip the contents of nanoc.zip, which would have been uploaded onto Blackboard. Create a new NanoC program. You can call the file yourprogramname.nanoc. In a terminal or CMD, type java jar nanoc.jar, your program name. The intermediate code file would have been created. Now, in a terminal or CMD, type python runtime/runtime.py and then your program name.nanoci. You should see the output of your NanoC program on the console.
Thank you, Vipul. My name is Prabhanjan and I will walk you through some of the NanoC language characteristics. Now, NanoC is a statically typed language, and NanoC provides two basic data types called integer and boolean. And we also provide two compound data structures called arrays and stacks. And the NanoC follows a block scoping structure, which means just like the C programming language, the blocks begin with open parenthesis and ends with closed parenthesis. And the NanoC is a dynamically scoped language. It allows recursion function calls to the use of call stack. NanoC provides simple if, else, and loop constructs. NanoC supports PEMDAS operator precedence. And this is the sample grammar. This is the grammar that you can see. You can see the project that is hosted on github.com/prabhanjan2906/compiler. This is the grammar. So as this is the starting point of the grammar. So as the name itself says, the program consists of declarations or assignments or stack statements or print statements or any function definitions. The declarations can be either a simple data type or a compound data type. So that is arrays and stacks. And the functions begins with a keyword called define and followed by the any function name and opening and closing parenthesis and optional any number of parameters. And the function returns a data type with something called return keyword, and the function has a function body which is nothing but declarations and sequence of statements. Now the sequence of statements can be one or more statements, which can be either be simple statement or compound statement. A simple statement is nothing but a return statement, assignment statement, or stack statement, or print statement, which you can see here. And the compound statement can either be a if statement or a loop statement. Now if statement begins with any number of declarations and sequence of statements, and if statement is nothing but if expression, then the statement of body follows within the scope, and otherwise if an expression, otherwise this. And the loop statement is not the other kind of compound statement is nothing but the loop statement, which can also be declarations, a sequence of statements, and loop break statement. Now loop so as I said, the data types that we support are integer and boolean, and compound data types arrays and stacks, which begin with the respective keywords, and the operations that we support on the stacks are push and pop. As you can see, this sample program, we have depicted a sample program in a file that ends with .nanoc. So it's like this: the define a function name and any number of arguments, returns int, blocks begin with parentheses, and you can see loop is the keyword for loop, and any number of statements or expression, and the function returns this. And this is how you invoke the function. So this is the named arguments we are supporting, so this should correlate with the function whatever. The Antler 4 generates lexer and parser and an interface that will implement the listener. So we have written a custom class called PVAP compiler interface interface implementation that implements the PVAP compiler listener that is generated automatically. So like we see, for every rule we have enter and exit functions that is generated by Antler automatically. So this is how, as you can see, for we are generating the bytecode inside the listener. So this is how we generate the bytecode, and you see for every statement we are generating the bytecode. So this slide explains what I just said. It's basically like the enter and exit programs are for example a rule. The Antler generates two functions like this, and we are overriding these functions to generate the bytecode.
Thank you, Prabhanjan. Now I'll be taking you through the through some small sample programs. In this program, we will be calculating the factorial of the integer 7 using recursion. So as you can see, we've defined a function called factorial. It returns an integer, and if the base case is 1, then if the base case is 0, when it becomes 0, you return 1. Otherwise, keep returning n-1. In this way, when we finally return, we multiply each factorial and we finally get the answer. So I'll execute the recursive factorial code. As I said before, you start with this line, which is Java jar. Now the intermediate code has been created, and then you start with and then you run the runtime, the Python runtime on the intermediate code. So the factorial of 7 was 5040. So this is the intermediate code that was generated when we ran the command Java jar. You can see that the function has been declared. We open scope. We see jump statements such as here. We see push statements, declare statements, and so on. So this is another sample program that is used to compute a base to a certain power. For example, if you want to compute 4 to the power 3, a function is declared, calculate power, a loop is declared over here, and then it keeps multiplying the base by itself until the expression is while the expression is greater than 0. So I will run the power program right now. The intermediate file has been created, and then we run the runtime on the intermediate file. So it will run for 4 cube, which is 64. So the final program that we'll be showing you is used to test arithmetic operator precedence. We'll be testing nested parentheses. A value of x is taken, which is equal to 10. And according to this, the value should be 10 minus 5, which is 5 plus 1, 6 divided by 3, which is equal to 2. In a similar manner to the previous programs, I will run the precedence program. The intermediate file was created, and now I'll run the runtime on it. So as I said, the answer was 2. So now that we have seen the sample programs, let's move on to the NanoC runtime. The runtime was developed using Python 2.7. The intermediate code is read from a NanoCI file and stored onto a list. The runtime uses a simple stack-based machine model as well as using dynamic scoping to retrieve symbol values. That is, symbols take values in the order that the functions were called. So you can see the entry point of the runtime system over here. The runtime system starts by first creating a global environment and appending it to the global environments to the environment stack. We open the file program, the intermediate code, and we call a function read file. The read file function over here is used to read each and every instruction from the intermediate code file and execute those instructions. The current line numbers are stored as well. Depending on the instruction, we call a function interpret command. This interpret command function calls a module bytecode with the appropriate command. Within the bytecode function, we can view all the intermediate code instruction sets such as read, declare integer, declare boolean, store, push, print line, equals, greater than, lesser than, and, or, and so on. Now each line of instruction is converted into an instruction object type. The instruction object contains the command and the arguments of the instruction. The bytecode methods are executed as I've shown you the bytecode methods such as push, store, etc. An environment class stores data such as the symbol table, local stack, etc. for each environment. An environment stack is defined to manage scoping and function calls. The environment stack stores environment objects. A function call creates a new function environment which is pushed onto the environment stack. This is our NanoC program. Thank you for listening to us.